Hello, everybody. In this video, we are going to go through the solution of question 115 in calculus section of the course Math1151 at UNSW. For these questions, we need to remind ourselves intermediate value theorem and the Rolle's theorem. So first, let's remind ourselves what was the intermediate value theorem. We are going to use it for this question. Suppose we have f function, which is continuous on the closed interval, and we have z, which lies between fa and fb. Saying this could be two ways. Fa could be smaller than fb, then we have this inequality, or fb could be smaller than fa, then we have this inequality. These two inequalities can be said as z lies between fa and fb. So this is why we are not using this one or this one. We are saying exactly if z lies between fa and fb. Then at least one, there exists at least one c in the interval such that fc is equal to z. What it means geometrically. Before I talk about the geometrically, I would like to remind you, if you would like to use a theorem, you need to say first whether the conditions of the theorem, which are the assumptions of the theorem, have been satisfied or not. If assumptions are satisfied, then you can use the theorem. So it's very important. So you first, in order to be able to apply such things, first you need to say if it's continuous and this condition satisfied, then you will conclude that exists at least one c. What is geometrically? So we have an interval a and b. Whatever, assume that fb is smaller than fa. So fb is this line, fa is this line. So we have a rectangular range here. Whatever is happening, whatever the function is between that one, it needs to be continuous, which means there is no gap. From here to here, that must be no gap in the function, no gap point, no empty point. Okay, then the theorem says that there exists at least one c such that fc is equal to z. So z is a some number between fa and fb, so it could be somewhere here. Assume that we have z here, so z will correspond a line, right? Y is equal to z line. So that is the line, and we're going to look at this line and where the function intersects, and these are the points C. It could be more than that if we have only one curve, like if the function goes with like that, we would have only one C. But if you have a more regular function in that interval, for example, here we have 3 points satisfying this condition. This is intermediate value theorem. Mean value Rolle's theorem is a special case of the mean value theorem, and we are going to do the more exercise on mean value theorem later on. And when fa is equal to fb case is the when we put fa is equal to fb in mean value theorem, we get the Rolle's theorem. Again, we have assumptions of the f function. F function needs to be continuous on the interval a and b, and differentiable on the open interval a and b, such that there exists a c in R, such that the slope at that moment, the tangent of the slope on that moment, will be 0. This is a derivation at point C, but geometrically it means a slope. And the tangent at C, so f prime C is a tangent at C, it is equal to 0, means that slope is 0, means that the tangent is parallel to the x-axis. In this case, fa is equal to fb, so that we have only one line. We have interval a and b, and we are looking at this interval. And in this interval, whatever the function is doing, the theorem says that there exists a point, at least there exists a point here, such that it is equal to 0. which means that the tangent at this point, the slope of this line is 0, and this line, the tangent, is parallel to the x-axis. This means that if this happens, it means that it goes up and down. If you have only one line, then it is already satisfied. It's already every element, every point from here to here will be parallel to it. You can have some function here as well, some function here as well. But to have such a point means that you are going up and down. At least you have one up and down. And this point C is telling you that whether it is going up or down, you might have some other things. Imagine that you have some function is here like that. So this point will be the point of f prime c is equal to 0 here as well, right? Or it can go so far down too. You know, it could go like this too. So still, you have this point which is parallel to the x-axis, right? You have these kind of options for that. But the existence of such point tells us that there exists some increasing area and there exists some decreasing area for the function in that interval, right? The existence of C means there exists some increasing and there exists some decreasing areas in that interval. At least two, right? At least one each. Okay, this idea will help us to solve this particular question. And we are going to use that idea for this question. Okay, now what is our question? So we have a polynomial, x cubed plus x minus 9. We would like to prove that this polynomial has only one real solution. For this, we need to find out the stationary points. What are the stationary points? Stationary points where the function derivative is 0. And this is not, you don't need it for this question, but I would like to remind you what is the critical points are. And sometimes we use the stationary points. All stationary points are also the critical points. But there exist differences between critical point and a stationary point. Critical points could be the end points of the interval. Also, they are also critical points. And stationary points are critical points. And the points f function is not differentiable are also critical points. For this part, for this question now, we need stationary points. We need to find out when the derivative of this function, derivative of this polynomial is 0. For that, we will be able to understand whether is there a like pump like that, or is there any going up and down. This is how we decide. This is why we need to. So call this polynomial px, and then take a derivative of it, so x cubed 3x squared plus 1. And this is always positive. So this is always an increasing function. And there is no stationary point. If you make this p prime x is equal to 0, that will be imaginary part we get, because you would have x squared, 3x squared is equal to minus 1 over 3. So it's imaginary, it's a complex number. Imaginary part is non-zero. There is no real part that has no stationary point. Okay, there's no stationary point. This is what this conclusion. So we would like to understand, we would like to find out, in order to be able to use the intermediate value theorem, we want to find out an interval such that the 0 is between in that interval, so that we can use the intermediate value theorem. Because, remind ourselves, intermediate value theorem, so we need such A and B, such that 0 is between FA, F, and B, and then we would say there exists at this one C in this interval such that FC is 0. This is the case. That is equal to 0 for our problem. because we are looking at the zeros of the polynomial. So we are checking that. So p minus 1, we got minus 10. So we check p0 is equal to minus none. Check p3, for example, is 3. We could look at the others, but here we have this one minus 9 and this one. This one is negative, this one is positive. It means 0 is between them. 0 is between p0 and p3. So we need to we can focus on the interval 0, 3. As 0 is between f0 is equal to 9 and f3 is equal to 3. Then we can use, and also a polynomial. I think that's what I need to say here. P is a polynomial, and it's always, What we need to say here, actually, P is continuous on 0, 3, as it is as every polynomial. Every polynomial is continuous everywhere. I missed that one. Yes, this is an important part, and you need to say it. This is very important. You need to say it before. Since this is an assumption, this assumption has been satisfied, then we can use the intermediate value theorem. We can apply the intermediate value theorem. Then at least there exists one C by using the intermediate value theorem, such that fc is equal to 0. There exists a 0 in that interval. Between 0 and 3, there exists a 0. Well, if you come to think of it, and p0 is minus 9, and p3 is equal to 3, right? This is somewhere here. And this is always increasing function. It has to go through the z-axis, so it has to have a 0 here, 1. And we know that this has no stationary point, which means there is no up and downs. There is no up and downs. There is no inflection points. There is no change of the direction. There's always increasing. Then we can use the Rolle's theorem. Again, in the Rolle's theorem, it says P is differentiable. That's what we need to say here. Before that, we need to say P is differentiable. P is continuous on 0, 3, and differentiable on open interval 0, 3. Since this is happening, we can apply Rolle's theorem. So in your case, it is very important to say such things. It is very important to say such things in your case, because we'll look at such writings, such justifications, whether this person can be used of such things or not. So this is an important part to add your solutions. Yeah, I think that's all I need to say, because since we applied the Rolle's theorem, there is no up and down, so there exists only one C, that is fc is equal to 0, or C is a real number such that fc is equal to 0 is unique. That's all for this question. Yes, be careful when you are applying the theorem. Make sure that you're writing down the justification of the theorem. Thank you very much. That's all for this question.